Okay. Hello, everyone. Welcome to another talk in our webinar series for the Brazilian participation group of the Rubin Observatory's Legacy Survey of Space and Time. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on Linea's YouTube channel, Linea MCTI. Today, we have the honor of having one of our own principal investigators from the LSST Solar System Science Collaboration, Dr. Valerio Carruba, from São Paulo State University. Dr. Carruba's research is on asteroid dynamics, with a focus on close encounters of asteroids with massive bodies and secular dynamics in the asteroid main belt. Dr. Carruba, thank you so much for being so kind and having accepted to give us a webinar talk today on such an exciting topic. The floor is yours.
Thank you so much for the invitation, for having me here. So today I'm going to talk about some recent work we have been doing using neural networks for the identification and classification of asteroids in secular resonances. So this is really very large collaboration, at least for groups. We work with people from at least 10 different countries, and I really would like to acknowledge their contribution, especially people like Stefan Regibai, Zoran Nezevic, Max Malke, Joseph Maciero, Fernando Roig, among others. So for those of you that are not familiar with asteroid dynamics, asteroid families are a group of asteroids that are formed by a collision or fission event. We can identify them in proper elements, which are different from osculating elements because they are constant of the motion. From them we removed the perturbation from the planets. And asteroid families appear in this domain as groups. So you can see here in the lower plot, semi-major axis, sign of inclination versus semi-major axis plot. And some of the largest families, like the Vesta family, the Maria family, the EOS families appear clearly as large clusters of asteroids. So asteroid families can interact with mean motions and secular resonances. Mean motion occurs when there is a commensurability between the period of asteroids and the period of a planet. And they are very easy to identify in this kind of plots because they are vertical lines, essentially. They have V-shapes forms in these domains. So near the Vesta family, you have the 3-to-1 mean motion resonance with Jupiter, and then you have other resonances like the 5-to-2, the 2-to-1, and so on and so forth. But when you work with secular resonance, identifying asteroids in secular resonance is more difficult because in these domains, they have a more complicated three-dimensional structure. So for instance, if you see the EOS families on the right of the plot, you can see that there are two lines, a blue line and a red line. This is the same resonance, the Z1 resonance, but for different value of eccentricity. So different values of eccentricity, the shape of the resonance can be significantly different. So this makes visualizing this kind of resonance a bit more difficult. So what are secular resonances, in particular G-type resonances? So we have a pericenter in orbit is the point of the orbit which is closest to the main body, which is the Sun. So if there was just two bodies, like in the two-body problem, the pericenter position would be fixed. But because of perturbations from the other planets or other bodies, this position varies with time. So it describes a large circle, which is similar to the precession of Equinus for the Earth. So there is a long period associated with this precession of the pericenter, and there is a frequency associated with this period, which is called G. Secular resonance occurs when there is a commensurability between the precession frequency of the asteroid and the precession frequency of a planet. The most famous secular resonance is the Nu-6, which occurs when there is a commensurability between the asteroids and Saturn proper frequency. So what is the effect of these G-type secular resonances? They increase the eccentricity of asteroids. And this makes them susceptible to have encounters with planets, to be lost by a mechanism like in close encounter with planet, collisions with inner planet, or to be expelled because of close encounters. And it is well known that the nu-6 resonance is one of the most effective mechanisms for increasing the asteroid's eccentricities to planet crossing level. So it's also one of the most effective mechanisms to transport asteroids from the main belt to the near Earth regions. So this is one of the most well-studied mechanisms for this. But inside the nu-6 resonance, there is a stable island of orbits. So there is a population of stable objects which are inside this very powerful resonance. So you can imagine these kind of orbits like having a population of small bodies inside a very rapidly flowing river, like the images that we are showing here. So in order to understand what is causing this, we need to have a look at the topology of the nu-6 resonance, what is the eccentricity sigma plane, where sigma is the resonant argument for this resonance, which in this case is just the pericenter of the asteroids, the longitude pericenter of Saturn. So you can have different configurations, but essentially you can have circulation, which means that the asteroid is not in resonance, and in this case the resonant argument will go from 0 to 360 degrees. And then you can have two stable equilibrium points. You can have oscillation around 0 degrees or oscillation around 180 degrees, which is much more common. Oscillation around 0 degrees is asteroids.
Sorry, Valerio.
So if you have an oscillation around, yes? Oh, sorry.
You're breaking up. Can you
now?
repeat? Yeah, can you repeat that last part?
You have oscillation around 0 degrees, oscillation around 180 degrees. 0 degrees is much less common than the other one. So oscillation around 180 is much more common for nu-6 asteroids. Oscillation around 0 degrees is called align oscillation. In this case, it's called align because in this case, the pericenter of the asteroid, the pericenter of Saturn are aligned. Oscillation around 180 degrees is called anti-aligned configuration because in this case, the two pericenter are opposite. The difference between them is 180 degrees. They point in opposite direction. So how can we identify asteroids that are interacting with the second resonance? So we can do numerical simulations of these objects under the influence of planets. Then made plots of the time series of the resonant arguments, like we show in these plots. If the object is not in resonance, the resonant argument will go from 0 to 360 degrees, like for the case of 2, 3, 4 barbars. If you have an oscillation of 180 degrees, the resonant argument will oscillate around 180, like for 21, 653 David Wang. You can have oscillation around 0, like for the fourth case. And then you can also have cases because of matter perturbation that oscillate between circulation and libration. So until recently, the number of objects that we have to study was limited to maximum of a few hundred objects. So this could be done by visual inspection of this resonant argument, but this is no longer the case for a new database. Nowadays, we have the number of objects that can interact with the second resonance can be of the order of several thousands, 10,000, 20,000 or more. So visual inspection can be a very taxing method to identify these objects. It can require weeks or months of visual inspection. You also need to apply a double-blind procedure to avoid that different observers could produce So to avoid these kind of problems, we turned our attention to artificial neural networks, which are based on what we found in biological system. Is usually artificial neural network will have input layer, a hidden layers or more, and output layers. They share the same fundamental blocking of which are usually neurons, weights, biases, activation function. So when you work with a neural network, you need to train a neural network in order so that they can recognize patterns. And that means essentially changing the weights of the models and giving them enough data that they will be able to identify different images. So the first model that we use was the perceptron model, which is an algorithm for supervised learning of binary classifier. A binary classifier is a function we can decide whether or not an input represented by vector or numbers belongs to some specific class. And this can be extended for multi-class classifications like the problems that we are discussing now, which are on libration, circulation, or switching orbit between libration and circulation. When you want to recognize images, some of the most high-performing methods are the convolutional neural networks, which are a type of neural network which were designed to work with two-dimensional picture data. So what are they doing? Essentially, you have a matrix which represents your image, and you apply some filters. So the product of this filter, which is usually 3 5 by 5 or a number of odd combination of rows and columns, is applied to the image to give a result. And this will produce what is called a two-dimensional array, which is called the feature map, which will allow you to identify important features in your images that will make the process of classifying your image easier. So one problem with this is that feature map software capture the precise location of features in the input. And so if even a little adjustment will produce a different feature map. So you can use to avoid this problem a pooling layer, which essentially will work by obtaining the maximum of the mean of the number inside a matrix, which can be a 2 by 2 or more. And this will allow you to smooth out the result of the feature map and make them less dependent on the precise location of the features. So which is why convolutional neural networks are so powerful, because they are less prone to what is called in-class variations. Even if you have circulation, you can have small circulation with different amplitudes. So because of these features, convolutional neural networks can be more resistant to these in-class variations between the same class of images. So there are several models of convolutional neural networks. Here we're using 3 main ones, which are the visual VGG from the visual geometry group. They use several small filters, most mannotol convolutional layer followed by max pooling layer, and the most use methods, the most used architecture for VGG convolutional network are the VGG16 and VGG19. So these are the first convolutional network that can make the model weights freely available. So you don't have to retrain the neural network every time that you have new data. You can actually use just upload the weights and apply it to new data. And this set a trend which is still in use among researching the area of computer vision. So you can have the inception model. The inception model is essentially a stack parallel convolutional layer with various filter sizes, as well as a pooling layer with a 3 by 3 maximum. And then you can concatenate the output of these layers into one single result. And finally, you can have the residual network, which was introduced by Tate al. in 2015. This utilizes shortcut connection, where the input is transmitted to a deeper layer while remaining unchanged. And the residual block is a pattern comprising two convolutional layers activated by a review activation function, where the output input of the block are combined. And this is called a shortcut connection. So how do you know if your model is actually working correctly? You need to introduce metrics, and the two most common using metrics are the constant entropy loss, which is given by sum of Ti log Pi, where Ti is the truth labels, which can be in our case 0 for circulation, 1 for switching, 2 for libration, 3 for vibration around 0. And pi is the probability for the hit class, and this ideally should tend to 0. And the accuracy, which is defined by true positive plus true negative divided by all the data, is essentially a measure of the number of correct predictions that your method will perform. It should ideally tend to 1. So these models can have millions of free parameters, and one of the problems that you can have is overfitting. Overfitting occurs when your model performs very well on what is the training data, but if you change a little this training data, the performance is not not so good. This is because the model learned the fine details of the training data, but is not able to export to this knowledge to other data sets. This is called overfitting. You can see this happening in these plots where the difference between the metrics for the training and validation set is significantly increased with different epochs of training of the model. So to avoid this problem, you can use techniques called regularization. You can use data augmentation, which essentially perform small changes on your image. You can have rotation, symmetry with respect on axis. You can see this in the images of the kitties on the slides. You can have dropout, which is similar to what happens to the brain when you lose, when you have some minor damage, you lose some neurons. The new neurons can create new neural networks and can learn the task that all neurons were used to do it. And you can apply batch normalization, which means essentially you keep the output mean and standard deviation close to 0 and 1. So how do you apply this method in secular dynamics for asteroids? You can apply it first using a perceptron model. You first integrate the orbits of the asteroid under the gravitational influence of all points. You compute the time series of the nu-6 resonant argument or other resonant argument for other resonances. You obtain images of this time series, and you can see an example of these images in the figures. So you can have objects that are oscillating around 180s, objects that are in circulations, objects that alternate between circulation and aberrations. So usually what we do is run this simple model for 50 series of 50 images, obtain a linear classification of labels. When we have a large data set of labels, we can actually go past through, apply this method to larger neural networks to obtain a more reliable method for predicting labels. So for the nu-6, we fitted the VGG, inception, and resonant model with and without regularization for data set of images over as a resonant argument. We did it originally for the nu-6, also for another resonance, which was a mean motion resonance with Mars, the 1 to 2. For the nu-6 resonance, the VGG plus data augmentation plus the dropout was the best performing model, and you can see it in the third set of images that you have in these slides. So in this case, we can now apply assess the performance. You can use accuracy or F-beta score, which is a calibrated method designed to account for both precision and coefficients. So these models can actually have very high performance, accuracy of F-beta higher than 87%, which means that we are now able to predict the state of thousands of asteroids in seconds. Instead of having to go to the images visually in weeks, we can actually do this now in just a matter of seconds. So why should we care about asteroids that interact with secular resonances? Because they can provide information that are not available for other asteroid families. So for the nu-6, we study the groups that are inside these population identified objects. We identify the Hindenburg belt, for example, we identify the object associated with the Svea family. These are the black and red objects, where the red dots are the multi-opposition asteroids that don't have yet an identification, and that were connected to the family using machine learning method based on the proper parameter distribution. But then we also identify a new asteroid family, a new group, dynamical family, which is the 12988 Tiffanykapler, which was not known before. So this is a small group, just a bit more than 10 asteroids, but we can apply methods for dating this family, which are very precise. We can integrate the orbits of these asteroids in the past and see apply two methods which are called backward integration method and close encounter method. The backward integration method will check what is the difference between the longitude of nodes of an asteroid and the parent body, in this case Tiffanykapler, in the past. Ideally, if the family formed in the last 7 million years, you will see that around the age of family formation, all the differences should tend ideally to zero. The close encounter method is a method which is based on counting the number of close encounters in the past between the apparent body and member of the family. So you can see here, for instance, in the second plot, the histogram of number of encounters of between 12988 and another member of the family. So you can see that there is a maximum between 3 and 7 million years. So we obtain estimates of the family age for these asteroid families, and these methods can only be obtained, can only be used for very young asteroid families that are less than 10 million years. In this case, there is agreement, and there is an age which is 3.0 plus or minus 1.2 million years. And this is the first young asteroid family ever found in the Nu-6 resonance, which is an interesting result. Also because it allows us to obtain further information, which is not usually available for other asteroid families. Since these are objects inside circular resonance, there is a quantity which is called the K2 line quantity, which is given by square root of 1 minus a square, 1 minus cos I, which is preserved, which means that while the orbit of the asteroid will evolve with time, there will be subject to perturbation from other planets, non-gravitational effect like Yarkovsky. The quantity which you see, K2 line, is preserved, which means the distribution of this quantity is the same now as it was at the time of family formation. So we can, in this case, we can actually create several fictitious families and see for what distribution, for what the fictitious family, the difference between the current values of K2 line and the produced one is minimal. And run chi-square statistical method to compute this difference. So the spread in proper domain A, will depend on a parameter which is called the ejection velocity parameter, which is associated with the velocity with which the asteroid were expelled at the family formation. And applying this method, you can see that the ejection velocity field for this Tiffanykapler family was 15 plus 6 minus 3 meters per second. So this is a very unique family because it's one of the few for which we can actually obtain with high precision the age and the ejection velocity field. And this is was just the second asteroid family for which this method can be applied after the Nijima asteroid family, which was a subfamily of the EOS families in the Z1 circular resonance. Another thing that we can do for Nu-6 asteroids was sampling the TINA objects in the TINA family. The TINA family is a family that has been known for more than 10 years to be in the stable configuration of the Nu-6 by Carruba and Morbidelli in 2011. But now we found objects that are part of what we call a resonant halo. These is objects that are not identified as member of family by standard method like the hierarchical clustering method, but they're still part of an extended family which is called the halo, which is very common in the rest of the asteroid belt. However, this is the first ever recorded case of a resonant halo, of a family that is inside a stable island of a resonance which has a halo. So this was another results of this work of last year. So what I'm going to discuss now are more recent results, and this is all under consideration by Nature Communications. So this was the previous result were for the new 6 resonance, which is essentially the resonance of the G minus G6. But there are other resonances which are called nonlinear resonance, which are higher combination of these precession frequencies. The two most diffusive G-type resonance are the G minus 2G6 plus G5, G minus 3G6 plus 2G5, which has the green line in the AG plot you can see in the figure. So there were work by Waman et al. In 2018, which showed that these were actually the most diffusive resonance G-type resonances, and so we focus our attention on this on these resonances. We apply the same method that we discussed for Nu-6 asteroids for the two resonances. For the G minus 2G6 plus G5, we identify more than 1,500 numerical asteroids and around 389 multi-position asteroids, which are possible in the resonance. And this is, you can see them in the plot. The red dots are obviously anti-aligned vibration, which in orbit are yellow. The circulating orbits are black. So we don't have aligned orbits in this kind of resonance. So only anti-aligned orbits. So you can actually confirm the status of this object by doing simulation with the non-gravitational forces like the Yarkovsky force. And we can do the same also for the G minus 3G6 plus 2G5. You can see that the distribution in as and I is as usual complicated. It's a three-dimensional structure. Most objects for the first resonance are in the central main belt between 321 and 522 mean motion resonance, while most objects for the second resonance are found in the outer main belt between the 522 and 221 mean motion resonance. So we can apply once again the same method. We can identify groups that are inside this population of objects, and we identify dynamical groups. These are not necessarily real asteroid families. These are groups that can be a section of a family that interacts with the secondary resonance. They can be artifact of the method, but they can also be among these young asteroid families that are real that were not found before the previous method. So there are 8 dynamical groups among the 2 Nu-6 minus Nu-5 and 4 among the 3 Nu-6 minus 2 Nu-5. So this is the part of the work that was performed by Dr. Malke. We compare the physical property of the family member to that of a family background population, which we define as region that include object number and multi-position between plus or minus 5 degrees of inclination, 0.05 in eccentricity, 0.05 astronomical units. And we retrieve all physical parameters for literature using the database SS or the DNet, which is served for in EMCCA, which contains a compilation of data from more than 3,000 peer-reviewed publications. So we have information on astrospectra, colors, albedo also from Dr. Masiero from Caltech. We have a phase curve coefficient, which is a new method for identifying taxonomy and physical property of asteroids. And we did this for all the groups in our study. The 2 Nu-6 minus Nu-5 group tend to be associated with S-complex taxonomies, while the other one are mostly C-complex, and this is expected because in the outer belt we found more C-complex objects, while in the inner main belt there is a more mixed population mass. In general, this is what we found, very broadly speaking, but there are more detail in article which is currently under review. So once again, we apply BMSM for these groups, and there is one family in the 2 Nu-6 minus Nu-5 and one family in the 3 Nu-6 minus 2 Nu-5 secular resonance, which are actually proven to be young asteroid family. And these are the first case ever found in both resonances, the 5507 Nijima family, and this 17076 asteroid family for the 3-2-5. We can find ages that are very close to 5 million years for both families with small differences. And then apply a clustering method from machine learning that can identify clusters in domains of age, absolute magnitude. And you can see that there are, at least for the second one, two very well separate groups. For the plot on the right, the two asteroids with blue colors, these are actually interlopers. These are objects that have different physical property from the rest of the families. And our method also found to have different ages with respect to the rest of the family, which means that they are more likely not to be members of the asteroid family. So, in order to obtain estimates on the ejection velocity field for these families, we needed also to obtain proper element, but these are different proper elements. These are called resonant proper element, and for these two resonances, we had to ask the help of an expert on resonant proper element, Dr. Mesevich. There was a theory for the 2-6-5 secular resonance, but there was no theory for the 3-6-2-5 secular resonance to obtain a resonant proper element. So what are these? Milan et al. Adopted the amplitude delta E of libration in eccentricity, which associated with vibration of the critical argument to serve as a new proper element, since this amplitude exhibits a property of remaining nearly constant with time. Then numerical procedure is used to compute this amplitude of vibration, and this is filtered online to remove short periodic perturbation. Then the time series of filter non-singular variable as muted filter again with the dimension 100 to remain associated with period up to 75,000 years. So you can see the difference between standard proper element, which are in black, and synthetic proper element, which are in red. And once we apply this procedure, which only apply for the eccentricity, we can actually use these new values of eccentricity to obtain the conserved quantity for G-type secular resonance, which is the same as for the nu6. Apply the methods that we saw for obtaining an estimate of the ejection velocity field. And we found that, again, the ejection velocity field is of the order of a few tens of meters per second, which is typical of small asteroid families. For the 170,776 group, the ejection velocity was 20 plus 1 minus 4 meters per second. It was small. So, to conclude, the main objective of this work was to identify which approach modern available convolutional network model was less prone to overfitting and more efficient in predicting the labels of large asteroid dataset of asteroid resonant images. A regular IVGG model can predict the label of 1,000 asteroids for the nu6 secular resonance with high accuracy F beta scores. Inception models works better for the nu6-nu5. So each resonance actually is different, and these models will prove themselves quite valuable when there have been surveys will start to discover millions of new asteroids after the beginning of operations. So prior to this work, the only young asteroid families known in secular resonance configuration were the Zelima family, which is in the Z1 secular resonance, and the Tiffanykapler. So now we have found two more, which are the 5507 and 107,776. And we are now at the estimated parent body of this object is much smaller. We're talking about objects that are less than 5 kilometers, while the parent body of the Zelima was much larger. So the Zelima family is a very rare event because it's a young asteroid families that are probability of forming according to collisional models from Dr. Fernando Roig, of 1 in each in 3.5 billion years. But now we're assembling objects that are much smaller, that have parent body which is much smaller. It is an object that have probability of collision forming of less than 1 in 10 million years. So we have the trend is that once we are sampling more and more of these small variable populations, we will be able to find more and more of these asteroid families which are in secular resonant configurations. And as we saw in these talks, these are families that can provide a lot of information on the mechanism of asteroid families. We can find ages, we can find ejection velocity field with high precision. So we are very grateful for financial support from UNESP, FAPESPES, and Tiffanykapler. And this was a work that was done by the machine learning applied to small body research group. There is an article which is actually under review by Nature Communications. And if you have any more questions or in interest, you can send an email to the machine learning applied to small body research group email address, which is on the screen, or see the site, which is also available on the screen. Thank you very much for your attention, and I stop here to ask for questions.
Thank you so much, Dr. Carruba, for the very interesting talk. So now we have time for questions from the audience. You can raise your hand, or if you're watching us on YouTube, you can leave your question in the chat, and I can read it out. Also, if you prefer to put it in the chat on Zoom, I can read it out for you. Luan?
Hello, Professor Valerio. Thank you very much for this excellent talk. I have two questions. I'd like to know if you and your group, you are doing some kind of methodology to explore hyperparameters in the deep learning models, especially from the convolutional neural network that I have showed. And the second question is if this data are available for public.
Okay, thank you very much. They are both very interesting questions. So we explore a series of parameters. We are not actually doing automatic hyperparameter fitting, but we explored several values of free parameters for our models. This was done actually with old-fashioned method, just by applying the different parameters and see what to work best. More details are available in our paper. Concerning the second question, yes, of course, all the models, the codes, and also the weights for the models are available for anybody that is interested. For the new 6, the results for the new 6 resonance, this is already available on GitHub. The links is available in the paper. We plan also to make the model, the weights, and all the rest, all the data set we used for the G-type secular resonance for the Nature Communication paper as soon as we will finish the revision process.
Okay, thank you very much.
Other questions? I have a question. So you mentioned there are some interesting anomalies that can be found in the data, but you didn't mention which. Can you tell us a few, or can you talk about that for a bit?
Well, one of the questions that people ask is why do you need to use, why it is advantageous to use neural networks for this kind of, for identifying asteroid in secular resonances? Well, there are other methods that can work. If you are actually interested just in liberating asteroids, you can actually use methods that are based on determining the maximum amplitude of liberation, the mean, and there are methods based on Fourier analysis that will give you that. But the problem is that when you start to analyze the whole class of asteroids, you have these in-class variations between each type of class. For liberating asteroids, even if you are an asteroid liberated around 180 degrees, it collaborates with different amplitudes. So this can create some problems. You can have objects that have switching orbits, the phases of vibrations and then phases of circulations. The shape of these images can be very different from one another. So this is one advantage of having these deep learning models, because they are very flexible. You can actually train them to identify this kind of switching orbit much more easily than other methods. Other problem that you have is that when you do train a model, not necessarily a model that works for one resonance can be easily extrapolated to another resonance. Usually, it's because of this in-class changes between the vibration characteristics. A model that works very well for the Nu-6 resonance, for instance, doesn't work very well for the 2 Nu-6 minus Nu-5. So each resonance really needs to be studied on its own. And this can be time-consuming, but it's also a very interesting challenge. We learn a lot every time we study a different resonance. Does that answer the question?
Yes, thank you. That sounds very interesting. Do we have any more questions? Okay, I don't see any raised hands, and also no one from YouTube. So I think we can wrap up. The presentation will be available on our website and on Linea's YouTube channel. Thank you everyone for attending, and a very special thanks to you, Dr. Carruba. Everyone have a great day, stay safe, and I hope to see you all again in our next webinar. Thank you so much.